Welcome to our lectures on the DC microgrid and the control system. Today we shall continue with our microgrid control architectures. Our presentation layout today will be as follows. So, that is control architectures in microgrids. Then we shall take one special kind of control technique, that is called master slave control, and thereafter we shall discuss about peer to peer control as well as the hierarchical control or hierarchy control. So, let us go to first the different kind of control architectures of the microgrid. So, there is a basic difference between the control architecture of the basic grid, that is a conventional grid, and the microgrid. Compared with the conventional microgrid, microgrid has two different modes, that is grid connected mode and the islanding mode, we have seen yesterday class. So, microgrid should be able to operate reliably in the both the modes. So, that is the one of the intentions of the microgrids, and depending on the role of the distributed generations in the microgrid, the control architectures can be either of these three. So, these are master slave control, where one will be the pilot inverter or the pilot source, and other will try to synchronize with that. Other will have a peer to peer control, that is all will have some kind of flexibility, no one is given as greater priority, all will act with a synchronization with each other. And thereafter we will have hierarchical control, one will be given more importance than other, there will be hierarchies. So, that is called hierarchical control. Now, let us understand first the master slave control, and it is illustrated in the figure 1. So, you have a main grid, that is a distributed network, and here what happened, you have a master controller. This master controller essentially can be of the two kind. If it is in a grid connected mode, then it will go for the PQ control mostly, but there can be some exceptions, and if it is in the islanding mode, it will go for the V by F control mode, and it will have a master unit of battery and the distributed generations. Thereafter, you will have a power electronics interface, and this from this power electronics interface, it will take inputs of the voltage and current, and accordingly it will take decisions. And so, this is the main part of it, and these are auxiliary control or the slave control. You will have VI measurement and the power electronic interface of DG1 and so on, and it will follow this master controller in toto, that is in a PQ controlling mode. This is we also have another generating unit or the energy storage unit. So, and also you can have a load with the controller with a load shedding scheme, and thus also you have a provision of the measurement of the V and I. So, thus what we can say, when a microgrid operates in islanding mode, either the DG or ESS of the master unit will take V by F control, because flux remains constant at that case, role to provide the voltage and the frequency reference for other DGs and other ESS within the microgrid. So, ultimately it will decide whatever V by F ratio has to be fixed, and all those entities will follow it. So, that is called the master slave control, and it is in a off-grid mode or islanding mode, it will go for the V by F control. And meanwhile, the other DGs are in a PQ control mode. So, they will actually inject the power and control the, since it main is V by F, other will maintain the require reactive power and the real power in the system as desired by the V by F. The controller with V by F control method is named the master controller, while the other controllers are the slave controller. So, only the master controller will work and set the frequency and the voltage of the bus, other will follow and maintain the PQ control to maintain those entities. Slave control take the corresponding action based on this master controller. However, microgrid operates in grid connected mode in most of the situation. So, generally when you have a grid disturbance or non availability of grid, then only it becomes a microgrid and isolates itself in islanding mode. When grid is healthy, mostly it is desirable and advisable to connect with the grid, so that you can dispatch extra power which you have, and generally what happens always you have a mismatch between the demand and supply, and you will be utilizing your storage element for that purpose. It is better to advisable that less you use the storage element, and for this reason it is also advisable to connect with the grid. And so, in that case when it is connected with the grid, in such cases the main grid provides the voltage and frequency, and thus your master controller will have to operate in the PQ mode. Frequency reference of the microgrid. So, all the controller within the microgrid will be in a PQ control mode. So, this is the basic difference in case of the islanding and the grid connected mode. Now, if a fault occur in the main grid side, the microgrid can seamlessly transform its interconnected to the islanding mode, and it will change it itself. That is what it is, a non availability of grid or any disturbances. So, it will change over to this off grid mode, and one of the DG's control, that is the master unit, must switch into the VYM mode, and that is predetermined. The commonly used master unit can be divided into the three categories. It can be the energy storage element, battery bank, DGs and ESS integrated with the DG, mostly solar and battery bank sometime, because solar may not be available at the night. So, for this reason this configuration is preferred, and also it may be so happen if you have an energy storage element, if somehow the battery lifetime is less or something like that, then also this mode is not suitable. For this combination of the DG and ESS is chosen for the master controller. If that is what I am writing here, if ESS is used as a master controller, the microgrid cannot operate in islanding mode for a very long time, since ESS keep discharging, and while eventually it will go out of power, and unless you have the excess DG generation to support you. If DG distributed generation is used in the master controller, the voltage frequency can be regulated easily. So, microgrid can operate in the islanding mode for a long time, but there is only one catch, the availability of this DG power. So, if it is solar, all of a sudden you got a cloudy day and your DG will not generate in output, then there is a very big problem there. And if you set it as a in a PQ control as a master controller. And for this reason, this method many researchers are preferring is to both DG and ESS as a master controller. This method works for the renewable generator, for example, PV, solar photovoltaic and the wind turbine. Due to the intermittency and the stochastic natures of the renewable generation output, ESS can help to reduce the voltage and the frequency fluctuations, so that the microgrid is able to run in islanding mode for a long time. So, that is the desirable features, and many microgrid follows and adopted that aspect. Now, if the energy capacity of ESS is large enough, but that comes with the cost, please keep in mind. It can set as a master unit or the V/F mode to offer the specified voltage and the frequency support for the islanding microgrid and adjust the power output to bring the frequency and voltage back to the schedule values. So, that is something you have to keep in mind if you want to make your storage element as a masters, capacity of the storage element will be quite big. If the energy capacity of ESS is small and limited, so generally this will be there as a practical problem, and it can be integrated with the decoupling of a certain renewable sources such as the combined master unit of V/I control to provide the desired voltage and the frequency support for an islanding mode. So, that is the combinations of the DG and the ESS. In this case, the coordinated V/F and the PQ control strategy is required to realize the frequency regulations of the microgrid mode. Then maybe this one is running in a V/F control, but the DG may be running in a PQ strategy, that is also possible. So, now let us come across the advantage and disadvantage of the master slave. The master slave control method has some disadvantages. One aspect that it should communicate individual DGs and ESS, and thus you require a faster communication channel. So, what does it say that it needs many communication channel as well as it requires to be fast channels between the different controller, which will increase the cost of total, or that is called capex, increase the total cost of the microgrid. The communication has to be proper and it has to be communicated with all those subsidiaries. It is difficult to apply master slave control method to the large system because one to many connection will be there, and implementation of the master slave control method has strict requirement for the communication and the supervisory control. So, that is something we require to invest, and not only power electronics, communication engineers and the communication aspects takes a big part of it. Now, let us talk about the peer to peer control. So, all are equally weighted. So, what happened? We split it out microgrid into some nanogrids here, and individual all have a control. So, whenever there is islanding mode, so you have a local load and generally you have a droop controller, and that will actually talk with the power electronics interface, and thus you may have a PQ control and you may have a energy storage and you will feed the local load. Same for here, there is another nanogrid, so it will talk with each other and ultimately will form another small nanogrid, and there can be a common load. So, it has to be connected, whosoever this microgrid will have a power surplus will fit the common load. So, individual control and feeding of the local load is a headache of the local control, and only to meet the demand of the common load they have to talk with each other and understand that what kind of power situation they are having, and only the among this microgrid which has got a surplus power, that will fit the common load. That is the way of working on it. So, it uses very simple technique, that is loop control method. Using the loop control methods, designated DGs and ESS are capable of adjusting their power output based on the locally measured voltage and the frequency. So, we need not have to have a centralized control over the whole microgrid. Individual portion of the microgrid can have a different voltage and the frequency. That flexibility it can have. Any large change in the load can be actively shared among the selected DGs and ESS unit based on the individual droop coefficient, so that power balance between the generation and the consumptions is re-established in islanding operation. Similar to the frequency droop control, a traditional synchronous generator, this peer to peer control belongs to the error frequency regulations. In case of the DC microgrid, it will be voltage. In that, it allows the some frequency and the voltage deviations from the desired level, and this concept also can be applied to the DC microgrid. Now, what happened? Compared with the master slave control, peer to peer control enables each DC's distributed generations and ESS to automatically participate in the power output allocations, which facilitate the plug and play function of the DG. That is one of the major advantage of the peer to peer connections. It allows plug and play type devices. So, you can add on and you can get rid of any load at your wish and without having much problem in overall microgrid, and that aspect is generally missing when you have a master control. So, master control has to accept that communications, and we got to have a processing whole unit, and thus what happen, it will take time to establish control and monitor. Meanwhile, there is no change in droop control strategy for distributed generation and the energy storage, that is BESS, regardless of the microgrid operation mode. So, depending on the whether it is in a islanding mode or it is a on grid, it does not matter, droop control will work according to the local frequency. So, seamless switching between grid connected and islanding mode can be easily achieved here, and that is actually less complex, because whenever there is a changeover off grid to on grid, so you have to change the mode of operation of the master controller. Here there is no requirement, since it works with the droop control method, it will continue to work in a droop control method. In practical microgrid applications, with peer to peer control strategy mostly is used and preferred, and some DG can still adopt PQ control to realize the maximum power point tracking and unity power factor operation, others for this other requirement. So, it can go for it, other can go for the peer to peer control. Meanwhile, the DGs and ESS unit rely on the deep control to undertake the power sharing task. So, which will sink the power, which will take the power, that aspect like what you have seen in case of the parallel operation of the alternator in your basic electrical studies, same thing will be done by the droop control. And it is not only the AC microgrid, it is also for the DC microgrid. Instead of the frequency and voltage, you will have the voltage only, DC voltage. Though proper setting of the droop coefficients, through proper setting of the droop coefficient, the net power can be shared among the different DGs in order to achieve the dynamic power balancing and maintain the voltage and the frequency within the acceptable range in the islanding mode. This is one of another flexibility of this peer to peer control. So, you have a droop control, and thus you can actively share the different kind of load, and you can vary this voltage and frequency within a limit, and thus you can have acceptable range of operations within that. Same features can be extended to the DC microgrid also. The controller in the peer-to-peer control architecture can make decision using local information. So, that is like taking information from the horse's mouth. So, you are not sending the data maybe the kilometers apart, and thus what happened, which can save lot of money during the establishing the communication system and also minimizing the system complexity, because it will talk in a local loop. In addition to the control method, can we fulfill the requirement for simplest transmissions between grid connected and the isolated mode, and thus changeover is quite faster and easier and simplest. For this reason, we say that peer-to-peer control can be applied easily for any plug and play network. That is one of the major advantage of peer-to-peer network. Now, let us talk about another method, that is called the hierarchical control. The hierarchical control, a central controller is implemented to use and send the control signal to the each distributed generator, electronic storage unit and controllable load. The two layers structures illustrated, that is BSS control element, DG control terminal. Now, you have distributed generations, protection control measurement, input and the outputs. Now, control terminal, network communication port, monitoring control, thereafter you have a consumers. Now, you have a control signal. This is the brain of the hierarchical control. Now, you have measured this all the signals, demand and the supply plan. You see that what you get from the sources and what is the demand or the load at the time. Now, there is a load tracking control, that means that it will actually say that how much load to be fed. Then there is a real time operation plan, and there is a operation plan in general that has been prefixed. So, you define the operation mode from that point of time, then you got a control mode, and but it can override by the real time operation plan. Say you have a data forecasting that some amount of irradiation will be there that time, and thus this will be the generation forecasting. But and accordingly you have then chosen the operation mode, but all of a sudden you found that actually you got a problem in the grid and you require to go for the offline mode, and that is the real time operation plan. So, you have to change the plan, and this is the hierarchical control. So, let us understand that how does it work. The first objective of the central controller is to predict the load demand and the renewable power generation. So, a set of operations plans is divided accordingly. Based on the collected status information including the voltage, current and the power, the operation plan can be updated in real time to adjust the power output and determine the start and the stop of DGs and the loads and the ESS unit. So, all those things has to be the state of charge of the ESS units, that how much local generation is there and what is the forecasting, all those issues has to be captured here. In this way, the stability and the voltage and the frequency, and in case of the DC microgrid, it is the voltage is ensured and relevant protections is provided for the islanding mode. So, let us see this figure 4. So, this is your main grid, and you have a main controller, and main controllers will work with the DG and BSS and power electronic interference VS requirement. Thereafter, it will sense the signal to this local load and the sources. Same way, you have another central controller that will actually give you the measurement of the PQ and the voltage measurement, and that will set to control another set in a PQ setting, and another microgrid that may be consisting of the loads and the A. So, it will go for the load shedding scheme. So, it has a different kind of hierarchy. So, this will have a main control, ultimately it will have a PQ control that will be desired. Here you will have a load shedding scheme. So, you can split it like that. So, not all this my nanogrid will be given a same kind of task, you will be differentiate the task. So, hierarchical control is one way, is one of the way of this master step control, but we apply a different kind of control to the different microgrid. In hierarchical control scheme, the physical communication channels are required for mutual communication between the DGs and the stop level communication. So, it is not the communication channels are missing. So, that is what I am saying, it is one of the way to the master step controller, but there is a little difference in between. If one channel fails to work, the entire microgrid fails to operate normally. That is one of the vulnerability of this kind of hierarchical microgrid. If main channel fails, everything will go down, shut down. Another type of the hierarchical structures are two layer control structure, that is generally preferred, and that gives the redundancy and the flexibility. So, that is shown in the figure. This is a main controller and there is another is a central controller. So, some will be given a task to PQ control and other issues, some will given the load shedding scheme, and they will talk with each other definitely sometime, but task is segregated, and if one channel fails, still you can operate this microgrid and still you persist to keep operating. In this control structure, weak communication is needed. So, you do not have to take a very fast bandwidth communications to coordinate the central controller with the local controller of the DGs. In this method, transient power demand supply balance can be achieved by the two level controllers. These are distributed generations, and the top level central controller are acceptable of modifying the steady state operating point of the two level distributed generations and managing the load based on the variations in both distributed generated output and the load demand. Even if the communications fails, if data is lost for the short time, that does not have any problem. So, fails for the short time, the microgrid still maintain the normal operation during the fallout time period. So, this is the hierarchical control. Figure 5 shows the same. This is the management layer, operation and the system distribution grid that depends, that works mainly on the predicted datas, and accordingly you set the mode. Thereafter, you got a different kind of microgrid. Thereafter, you got a low voltage side, and in between you got a one microcontroller, one this controller. So, there are so many controller. With that there is a local layer, and this layer is an optimized layer, and accordingly you can switch on a different mode and will decide which layer to be considered. So, based on these discussions, what we can say that the middle level microgrids in charge of the monitor and operation of substations as key to the node voltage of frequency of each microgrid in the islanding mode, power flow through the each branch of the current output, and the power reverses the margin of the each DGs, and the coordinations between the load and so on. This has been done by the middle level. In addition, this kind of microgrid can optimize the economic operation of each individual microgrid and provide ancillary service through the proper regulation of the ESS and DGs, including the load flowing, operational reserve, as well as the frequency regulations and the voltage control. And moreover, the bottom level, the local control consists of the micro source controller for the DGs and ESS, as well as the load controller LC, aiming to ensure the transient power balance if there is any certain mismatch of the power. So, that will ensure that transient power balance, and it improves the power quality problem and the dynamic load management. The complete hierarchical control strategy can be realized through the multi-agent system, which in abbreviation we said is MAS, which comprises of the main grid agents, microgrid agents and the micro source agents. Thank you. Thank you for your attention. We will continue our discussions with the different hierarchical topology of the microgrid in next classes.